Great. Bianca, thank you. Thank you very much. I think you'll see what I have. I have an agenda up on the screen. And so, yeah, let's begin. As I mentioned, my name is Judy Sandrock, and today we are conducting an onboarding workshop for our CubeSat kit and hosted by MaxIQ. As MaxIQ, XinaBox is one of the products that we do market and one of the products that we do currently support. Bianca is not only a major shareholder of MaxIQ, but he's also the inventor of XinaBox. So if there's anybody who can answer your questions, it's going to be Bianca. So Bianca, I think what I would like to do is maybe what we do is maybe we have everybody just introduce themselves and where they're from. I know that we have people, we have certainly participants joining us from Botswana, we have participants from Europe. So maybe if everyone just introduces themselves, and then I'll hand over to you, Bianca.
That's cool.
Excellent. Professor, should we perhaps start with you? Professor Basutli, are you there? I was just wondering, perhaps we start with you. Okay. Anybody else want to introduce themselves? Otherwise, we can go straight into the workshop. I see a message from the professor. He's saying it's failing to unmute for him. So that's interesting. I wonder if it's got something to do. It can't be.
Hello. Yeah. Now I'm on unmute.
Wonderful. Excellent.
Okay. All right. I guess I've introduced myself before. My name is Bokamu Sobasutli. I'm a lecturer at Botswana International University of Science and Technology. And I'm here with my students to attend this workshop.
Fantastic. Fantastic. So everybody has their kit.
Yes, they all have the kits with them.
Wonderful. That's absolutely amazing. Maria, is that you that I can see also on our call joining us from Valencia in Europe? Okay. I think also maybe there's just a little challenge there with unmuting. Bianca, yes, what I'd like to do is that I'd like to, may I hand over to you to introduce yourself, maybe briefly, and then also to take us through the fundamentals of the kits, the ground station and the flight station.
I will do so. Judy, just before I start, is it Xq7 or Xq90?
Xq90, the CubeSat kit.
Okay, that's good. Okay. Yes, so hi everybody. You can hear I speak with a slight accent. Actually, somebody will even say a strong accent. And that's because I was born in Denmark many moons ago. And I lived in South Africa the last 20 years, since 99. And I actually spent a good part in Botswana my first year because getting my citizenship and things like that didn't allow me to work. So I traveled around in Botswana from all the way in the southeast to the northwest to see the cave drawings and etc. Anyhow, I'm here to talk about something a little bit further from Earth, satellites, and we have a kit. So assume you all have had an opportunity. Have an opportunity to play with the X chips, as we call them. So I'm holding up a few X chips I just randomly put together, and if you haven't put them together, then don't try to do it now. I mean, you can of course play with them, but rather maybe follow what I'm saying and especially follow the instructions. So there's not much to it. I think the important part, and let me just take two X tips here. So I'm gonna take a GPS, and I'm gonna take a core. So the CS11 is a core, and that core is actually exactly the same chip you'll find in Arduino Zero. And I think I have one right here. So this is Arduino Zero board, and this is our version. And if you look at this little black chip here in the middle, you will see that's exactly the same as this one that sits here. So these two are the same. They are AT-SAMD21G 18J or something like that, but they're exactly the same. So they're Cortex M0 cores. They have they run 48 megahertz. They're 32-bit style cores, and you don't even have to install anything in Arduino if you want to program this one here, other than if you want to program the the Arduino Zero. So this is kind of like the same. You can see ours is considerably smaller than this one, and that's because this one have some other chips on it that allow you can program with something that's called a native port and a programming port. And we have neither, because we have it in a separate module, either the IPO2, which I have here. And when you program the IPO2, you have to have a small sensor here, a small connector, and that connector allows the USB from here to connect to the chip that have onboard USB. We also have another programmer that's called IPO3, and that looks like that. So there is a micro USB. So that's the same as you can see here in the Arduino Zero here. So now it starts becoming maybe not the same size, but you get some of the same stuff. And we have another thing that the Arduino Zero doesn't have, and that is there's an SD card holder here in the back. So you can write the data to the SD card. We also have a RTB LED, so RTB for red, green, and blue. Red, green, and blue. And this one have just a single, I think, yellow LED. So yeah, so that's a difference. On the other hand, this have a lot of connections here and there. We only have the connection via our standard bus, but that's the whole idea. We want to get away from breadboarding and soldering and all that kind of stuff, and focus on very quickly just to click some projects together. The last way you can program this thing here, and that's a default way when you buy a kit, is you put the software on an SD card, and then you just plug the software into you plug the SD card into the you plug the SD card into this one here. So you take your SD card, you plug it into a computer, you put the bin file on it, update.bin file, and I'll get back to that. And then you put the SD card in here, of course, power it up. That can be either with battery module you got, it could be with the IPO1 that you have, like for example, I have an IPO1 here, use on a ground station, whatever you want to do. You can't program it with IPO1, but you can power it with IPO1. You can power it with the PBO4 or PBO2. There's a lot of different power modules. So that's a core. When you connect it to another sensor, then what we have done is that we have a communication protocol that's called I2C. It's not ours. It's been around since, I think, 35 years. So it's a 2-pin communication protocol, and it's the only true bus communication that exists out there. So the way it works is that the data flows on one pin, and then the other pin is a drum. It's a clock that being sent from the core, from the master, to all the different devices. And that will kind of like determine the speed that the data comes in. there can only be one master, and everybody else is then listening and responding to the master's signal. The way it works is that you send out an address and say, if you have that address, please respond to me. So they do that. There's all a communication protocol like SPI. There you have to have a dedicated pin for it, so it's not a true bus. There's USB and Ethernet and all that kind of stuff, but they only work pin to pin, and then you have to have a hop in between and so on. So I2C is the favorite, and that's the reason why we use that everywhere. When you click it together, there are very simple rules. There are two rules to follow. The one is that you should be able to see the name on the same side. So here is the name here. So we have the name here, SN01, and we have CS11. So even though that you can maybe click it together, you know, front to back, it will not work. It's not going to fry anything, but it's just not going to work. So if you need to have it working, which you of course want, you have to click it together so the name is on the same side, like that. So that's one rule. The other rule is that you have to make sure that the connector aligns. So you can see there's a little tab, and therefore you can click it together. This is still fine, even though that the name here is an angle to this one here. But you will see you can't do it on all sides. So in this one here, this is not going to work because that tab is, you know, second from the top, and this is second from the bottom. So you will fail here. You will also fail on that side. But if you put the connector together like that and find another side, and there will always be two sides that works to any other side on your chip. So that's the rules for putting together. I suggest when you put it together that you hold the edges like that. It doesn't really matter for most of the chip if you hold on top of them. But if it's a sensor, you might actually block, put a little grease from your finger on the sensor. And if it's like the display, you might actually cut yourself or break the display. The corners are very fragile, but so therefore hold on the edges when you click it together. Whatever way you can kind of like find it to put it together here. Let's see if we can find another angle here. There we go. So that's how it's put together. Now the kit have two circuits. So for me, a circuit is when you click a number of X tips together. So there's one circuit, and then you have another circuit. And what you have is that you have a ground station circuit, and you have a flight station circuit. And we referred that to GS for ground station and FS for flight station. So when we originally did this kit here, it was to kind of like simulate the Xq7, by the way. So Xq7, the difference between Xq7 and Xq90, it have some of those expensive connectors that allow you to interface it with other CubeSat stuff. So I'm gonna talk about Xq7. It's otherwise the same. There's just like more connectors on Xq90. What I'm gonna do is that I'm gonna talk about the Xq7 style, and then I'm gonna go over to Xq90 after that. Before I do that, I just want to share a screen here, which is going to help you a lot. And this is this getting started here. And Judy, just give me a thumbs up if you can see my Chrome screen here getting started. Okay, good, thanks. So this getting started here. So there is a link here. I think Judy have, maybe I already put it into the chat. But you can see here, there's a table of contents. We talk about the flight station and a ground station. And then I have this CubeSat addendum here, the Xq90, and a little bit of troubleshooting. Now this page is your go-to page. This is where all the stuff is. There's a video here. You can see there's a link to a video. So what I suggest is you read this thing here very, very, very carefully. It's not super complicated to put together. And of course, I can put it together like in a matter of, 10 minutes or something like that. But what I always suggest is that if you want to put it together, you better spend if you want to, for example, fly it on a balloon, you gotta have to spend a week in preparation before you can get it out on a balloon. And I'm gonna go through some of those things in this example here. So what I want to do first is I want to actually go through this document, because that's like the document you have to lean towards. So as we talk about here, there's a flight station, which is very similar to what I have in my hand. It's not exactly, but very close to. And you can put that on a balloon or a drone, or you can put it into a rocket. You can put it on top of a flag post. Yes, Judy? You're on Zoom.
Bianca, yes, Bianca, what we've done is that with MaxIQ, we have an identical copy of this page of this page on XinaBox. We now also have on MaxIQ. So I have I've sent everybody both links, the one to this page that you're demonstrating, but also we do have it on the MaxIQ website. So I just wanted to share that, so people didn't feel that you were showing them something that they didn't have already.
Okay, I mean, it's the same page, so there's no difference. So I can show it anywhere, it doesn't really matter. But allow me just to continue here if it's the same or otherwise. Okay, so so as I mentioned here with the flight station, you can, it doesn't have to fly anywhere. You can just put it like on a remote location. So you can put it like on a hilltop somewhere. You can drive around with it. The only thing you're gonna figure out, and that is how well is the connectivity between the flight station and ground station. If the flight station up in the air, it can read much further, and I'm getting into some of the details there. And then you have a ground station, and normally when you consider satellites and ground station, people have rooms for that kind of stuff. They have big antennas on the roof and all that. Your ground station is just 4 tips big, so it's like 6.5 by 6.5 centimeters, something like that. So it's not very big compared to what you normally see. On the other hand, we upload all the data to a dashboard, and then you can see all the data there. Okay, so I'm gonna go through the whole thing here, so I'm gonna skip over that. So the flight station, which is maybe the most interesting, is that you have the CS11, as I showed earlier, which is this Arduino Zero style core, Cortex M0 core. You can optional put an ODR1 in. So you only have one ODR1 per kit, and that's normally on a ground station. But if you kind of like want to debug, you can take the same ODR1 from the ground station, put it in the flight station, and see what comes out there. Or you can borrow one from one of your classmates when you try to figure out what's wrong if you have debugging issues. Then you have a IMU, so either SIO1 or SIO2. So that's mainly an accelerometer. On SIO2, it's also a magnometer, and SIO1, it's a magnometer and gyroscope. So the important part for this kit here is the accelerometer. And then you have a weather sensor, either SW1 or SW3. With SW3, it's a pressure sensor and temperature. SW1 is also pressure and temperature, but also humidity. Then you have a light sensor, which all give you ambient light, and it also gives you a UV index reading, similar to what's being reported on weather sites. Then you have an air quality sensor. Now, this air quality sensor will measure the total volatile organic compounds. So kind of like carbon-based stuff out there. Now, if you use it as an indoor air quality sensor, it will assume that there's people and normally household stuff happening or office stuff happening. So it will calculate a CO2 level based on that. So it's estimated CO2 level. If you use it in a factory and you have like benzene or other kind of like volatile organic compounds, then it can still come out and say CO2 level, but you can't really rely on it because it might be other volatile organic compounds that make up that reading. You have a GPS sensor here. So GNSS, and this GPS only uses GPS. It doesn't use GLONASS, which is the Russian system. It doesn't use Galileo, which is the European system. It doesn't use Baidu, which is a Chinese system. It doesn't even use neither Indian or Japanese system, wherever they are in a beta release of their stuff. Then you have a BPO1 or BPO4, so that's a AA battery power supply. You will have a radio, ILO 1, 2, or 3, and they run these different frequencies. Actually, ILO 2 and 3 run both the same frequencies here. So whether you have ILO 2 or ILO 3, they both do 868 megahertz and 915. I'm coming back to the radio here a little bit more separately. But the important part is that all these frequencies, these two frequencies in Europe and in Africa are license-free. They're called ISM licenses. A 434 here is also part of the radio amateur band, but it's still an open license in our end of the world. So Europe and Africa, Middle East, we belong to something called ITU Region 1. And in America, South and North America, so Canada, USA, all the way down to Argentina, is the Americas, and that in ITU Region 2, and they only allow this frequency. ITU Region 3 is the rest of the world, so Asia and the Pacifics, and they haven't been able to agree on common frequency. So we're not really supporting there. I believe that ILO 1 is actually 434 and also 470 megahertz, so they can use it in China and so on. There's an antenna. You should have yourself an SD card, so that's not included in the kit. And you can use any SD card as long as it's a micro SD card and it's maximum 32 gigabytes. It can't be bigger. These days it's getting more and more difficult to get smaller. But even if it's 800 megabyte or whatever, then it's fine, as long as it's micro SD card. And you need 2 AA batteries. And here's a step for preparing it. It's quite straightforward. You download this update.bin. So I'm going to open that in a new tab. And you can see here is the update.bin. There's also an update UF2 file one can use. Judy? Okay, cool. So this update.bin is what you download to follow the instructions. If you have a programmer, so like the IPO2 or the IPO3 like I have here, then you can also use the UF2. And the way that works is that you plug the CS11 into a programmer and into a computer. You double click on a reset button that sits here, and then the CS11 will appear as a drive on your computer. So it will say CS11 as an external drive, like a thumb drive, like when you have like one of these USB drives, it will kind of like see it like that. And you simply take this UF2 file and drag and drop to that. You can't do that with the update.bin. The update.bin is for programming using the SD card. Let's go back. So you assemble the flight station above, and it doesn't really matter how you put it together, in what order. You can make it in one long strip, you can make it as a T, but the reason why it's put together like that, I'm just turning it to the back side, is because that there's a redundancy the way that it put together. So let me just stop sharing here so I have a better screen. So when I, hang on a second here, speaker, there we go. When I have it like here, you can see that this connector here, so there's normally like a CS11 or something like that here on top. Let's just put a random chip in here. But you can see the middle chip here. Let's take it from back. Actually have 4 connectors all the way around. So that means that that any of these 4 connectors can fail and it will still work because it gets power and signal over it. So the connectors works both as giving it robustness, so make it kind of like hang together stronger, but it also redundancy. A thing that normally lacks in many satellite building is to just have 2 wires for power from something to something else. So like your power module maybe have, 2 wires to the GPS module, and if that fails, your GPS fails. On a satellite, it's not so good because you can't just pull over and get it fixed. If it's a radio or power that like lagging, then suddenly you just don't have any communication to it. So with this thing here, we have this redundancy here that allows you to kind of like say, well, I don't have to use that connector, or half of that can break, or another half of that can break, or whatever. So we have flown this thing here on balloons. We actually had it on a year or two ago. We had 3 satellites like this on a high altitude balloon, flying from somewhere up in the northern end of South Africa, and the parachute didn't unfold properly. So it came down with almost terminal velocity together with 11 other projects. And ours was still running when it landed, simply because it can take this vibration, because each of these connectors, they have, they both work as shock absorbers, because they can take a little bit move. And each components, because they're so small, it have the same thickness as your motherboard in a computer, 1.6 millimeter. But because it's so small, they don't bend. So you can't snap the copper lines and things like that. Put it together like that, this thing can bend and therefore give in for shocks. And you have multiple connectors, and therefore you have the redundancy. So with that said, also we had, as I said, we had 3 of these projects landing with almost terminal velocity on grass, and they all ran. We had the camera used connected to a Raspberry Pi Zero and a servo, and the servo arm broke on one of the others. The solar panel broke, but the circuit was still running and collecting data. We had 41 satellites flying on this thing here in 91. All of them, in 2019, in April 2019, they all got data, and they have to kind of like withstand the shocks and vibration from a rocket. Okay, let me get back to what I'm sharing here. So you can assemble, as I said, any way you want. If your SD card is not new, and this is very important, you have to format, and this is a link using this SD formatter. So this SD formatter, you can get it to Linux and to Windows and to Mac and to almost anything. It comes from the organization who are controlling the SD card format. You can see here Windows and Mac. There's a lot of different versions of this thing here for all kind of different versions of Mac and Windows. And the reason why it's important is because if you, for example, use this SD card on a Raspberry Pi, or used in a camera or anything like that, and you put it into your Windows or into your Mac and say, no, I formatted it and you can't get it to work, I'm not going to take your call unless you format it with this thing here. And you will realize that once you format it with this thing here, you probably get it to work anyhow. So I hope I said it hard enough. You have to format your SD card with this thing here if it's not new. If it comes straight out of the packets, then it's formatted with this thing here. That's the law from the SD organization, that everything has been pre-formatted with this format here. And there's 2 options when you format with that. There's the quick one, and there's the override one. The quick one is quick. It takes like a few seconds. And sometimes your card will work with that. If it doesn't work, you take the long one. It takes half an hour to format the SD card, but it overrides every single byte on it and makes sure it's properly formatted, and then it will work. The way you know if it works is that if you put this update.bin on the SD card and then plug it into the CS11, as I say here, then once you power up, and it says don't power up yet, but once you power up, it will then read this update.bin from the SD card, and it will delete it afterwards. So the update.bin will disappear from the SD card. If the update.bin doesn't disappear from the SD card, then your SD card is wrong. It's probably not formatted correctly. It's bigger than 32 gigabyte. It's not an SD card, whatever it can be. So I want to emphasize that also it can only write to it. And one of the reasons why it's so difficult is that that's it's program Arduino library for SD card is very specific. It doesn't use all the pins on the SD card. It only uses 4 of the pins plus power. So it uses SPI to write to the SD card, and that's like a standard thing here in the embedded world. So that's the reason why it's like that. Then if you have a 3D printer at your institution, you can print out a frame. So here is a 3D printable frame that allows you to, that's similar to a frame I think I have somewhere. Maybe I can't find it right now. But the frame is actually great for Judy have one there. So it's just a 3D frame, and you can see here's the frame that Judy holds up. So it's just a 3D frame. The corners are kind of like cut away, like you can see here, because that will fit inside a CubeSat, because the columns in a CubeSat is 8.5 by 8.5 millimeter. So that's cut away like that. And you can see there's some screw holes. Each of the X tips are 32 millimeter wide in both directions. That means it's 96 millimeter across. That leaves 2 millimeter on all 4 sides. And then you have 100 millimeter, 10 centimeter, which is the size of a CubeSat. So that's the one frame. There's another frame also. I think this is the generic one. Let's see here. So this one here, the other one fits inside a CubeSat. That was like the idea. This one here, you can see it have like these slightly bigger holes here. So it's wider than 10 by 10, but allows you to mount screw, for example, something across it if you want to kind of like put a PCB or something else across the stuff. Okay. And then finally, instead of using any of these frames, especially for your ground station, you can use our 3D Enclosure Designer, which allows you to design a box. And you can use that also for your flight station. So the way it works is that you have like a box here. Let me take it a little bit out. So you actually just say here, how big is it? Well, I have, for example, for my flight station, it's 3 by 3. So you just say 3 by 3 and you say update here. And then you tell in each of the fields here what you have in the box. And let's say, for example, number 1 here, we have a USB power. So power, USB, and number 3, we have LED. I'm not gonna go through the whole thing. And then number 6, we have a radio. So I'm gonna put radio, and I'm gonna show you what that does. Let's say number 4 here, I wanna put a text on. Text, actually, let me just put a icon on like that. And then I say update. And then what it does is that it puts a hole for the radio here, because the radio antenna can stick through here. It put a USB here for the USB power, the IP01. And then if I go over to this side, you can see there's a logo, and here's the window for the OLED. And when you kind of like finish with the design, you just say generate STL here, and it generates STL, and you can download the STL, and you can then send it to a 3D printer, or you can send it out to an external 3D printing service. So that's that allows you to very quickly do it, and it supports like rounded corners that look pretty. You can print out the box and the lid separately if you want it in separate STL files, because some printer don't like it if it's together. You can make it 3D print ready. It just flips this thing here around so it's upside down. It's a little bit easier because then the flat part is down, doesn't have a lot of overhang. And you can also depending on your 3D printer, you can see that if I go in here, there's a little space here between the pillar and the wall. That is this space, and that's just if you have a 3D printer that's not very accurate, like many of the standard FDM printers are, thing expand or it's not like super accurate, then you will want to give it like a couple of millimeter here, so you can kind of like mount it. The enclosure is the height, the standoffs is the height of these standoffs, and then the thickness of wall is 2, etc. If you have more that you want to put in, like for example number 8, you can simply just go in and say 8 here and 8 here, and then you can say, no, I want to have LED there, but also want to have, for example, a power LED or whatever it is, and then there's room for both. Play around with it, it's quite cool. And yeah, so that's your 3D printing functionality here. As I mentioned here, there is a ODR1, a display that you can add to it. I wouldn't recommend flying with the ODR1. It's fragile, but you can plug it in and before you power it on, and you can just plug it off when before you fly if it is, or you can reboot it without putting it in. OCR1 is a controller. I haven't really tried it. It's like a new functionality we added. And I don't think you have an OCR1, but one of the things that we kind of like want to try to add to the circuit. I just want to talk a little bit about batteries. I have added some batteries. You can use any kind of AA batteries you feel like, but if you go to a balloon flight, so for example, we've been flying in 12 kilometers altitude, and that when we flew there, we had minus 52 degrees Celsius. Okay, so for you outside Botswana and South Africa, yes, it gets cold here when you get far up. So minus 52 degrees. The batteries here, this is non-rechargeable lithium batteries. They can take minus 40, which happens to be the same in both Fahrenheit and Celsius, and that's actually fine. They were still operational at minus 52. If you take other AA batteries, well, you might not have them working at a high altitude. So just have that in mind. Of course, these are more expensive, but there's also a good chance that you're not getting your whole kit back. So then this is going to be a very small cost in the project. So there's a little story about the batteries here. Then I want to go to the ground station. So ground station is just these 4 chips. It's a core, which also have a Wi-Fi module on board, the CW1. It's based on the ESP8266, which is a very well-known Wi-Fi core in embedded world. It have the display, the IPO1, which is a programmer. So this one you program using our XinaBox uploader. I'll come back to that. And then a radio, of course, that talks to the flight station. So here what you do is you install the XinaBox uploader. There is a whole separate link about the XinaBox uploader. So I'm not going to go through that. I do think there's a video here in the bottom. There's a little bit of troubleshooting and things like that. And XinaBox uploader, it's not super necessary you all get it to work. So if some of you can't get the XinaBox uploader to work, some of you can, well then, help each other by, loading the software to the ground station using this one. So just because it doesn't work on your computer, it's just that this is made both for Mac and for Windows. And sometimes, depending on how old your computer is, you might not support the FTDI chip that sits on the IPO1. So there sits a chip like that on the back of your, or front, I can't remember, on your IPO1 on the back. And that you might need to install drivers and things like that. But if it gets too difficult, then I will suggest that you just help each other out. You assemble the above flight station software. Again, you can make a long string. You can make it into a little 2x2 chip cube. Plug it into the USB, open the XinaBox uploader, and you select it and drop down. So if I have a IPO1 here, So I'm just gonna quickly put it in because you have to plug it in to your computer first. You don't have to plug the whole kit in. So I'm just having something I can quickly plug in here. And then once I plug that in, I'm gonna start the XinaBox uploader. So let me stop sharing here. And then I'm gonna open XinaBox uploader. And once it's installed and working for you, then of course it's straightforward. So I'm gonna now share that. So you should now see a little square here, and you can see I'm running on a Mac here. So it automatically finds where it's connected. So if you're on a Windows machine, it will say COM1241, whatever COM port it is. On a Mac, a COM port looks like that. If you plug it in and out, you can click on this refresh where it's reload the port list. But what I suggest is just plug it in first and then start XinaBox uploader. And if it doesn't come up with something, it's because it doesn't see the IPO1 or it doesn't see the CW1. So that's two things. If it sees CW1, you can see down here it says CW1. It gives a MAC address. That MAC address could be important for you. I'm going to come back to that. And it's just a version number of this XinaBox uploader. It's been 1.1c for a while, so that's it. And then you choose the app you want to install. So there's a number of different apps. And one of the things that you could consider is install, for example, the Lighthouse first, just to kind of like try to figure that out. If you want to know about the Lighthouse, there's like an info button here. So if you click on that, it opens up the info, info in the browser. So we need to just open that. So my default browser is Safari, so therefore it opens here. And there's like, what do you need? You need CW1, ODO1, SLR1, and IPO1. So you take the ODO1 and CW1, IPO1 from your ground station. You take the SLR1 from your flight station. You put those four together. And there's a little video, and you kind of like have a little, let's call it hello world, that gives you an idea about how to get that to work. I'm going back to the XinaBox uploader. The one you have to install is the one called Xq7. And if you click on that info button, you actually get to the page I've been following so far. So it takes you straight to that. Once you have chosen it, you click Flash, and then it downloads the Xq7 from the internet. It's like a few hundred bytes, maybe kilobytes. And then it flashes it to the CW1. It goes considerably faster downloading it than when it flashes it to the CW1. It flashes it on kind of like the default speed because, again, it tried to make sure that everybody's computer can follow this speed here. So once it finished flashing this thing here, it comes out and asks a couple of questions. It's called provisioning. That's a standard in the IoT world. So say getting provisioning. So ask the computer, what do you want to ask the user? So all that is inside the code. And it comes out and say, I actually want, what is the Wi-Fi? So I go in and say XinaBox. And what is the password? Say Rapid IoT. What do you want to call the unit? So my name is Bjarke, but you can call it, university name, school name, individual name, red, green, or blue, whatever you want to call it. It's important that you call it something so you can identify it on the dashboard, because if you call it some, as everybody else, if you have 8 kids and you call it your university name, then you don't know which one is which one. And then which radio you used. Again, talking about these ITU regions. So whatever radio you have, if it's an ILR1, if it's an ILR2 or 3, you can just choose the one that's for you. So if you're in Botswana, it's 868, the same in Italy. You choose this one here. And then when you finish, you say, okay, and it writes the data to the core and I say ready, and that's it. Then you are actually finished with that piece of software. So let's get back to the page here. Okay, so I just have to say this thing here with the XinaBox number, it looks very simple. It looks very straightforward. It looks like something you should be able to handle in a few minutes flat. And if your computer can read the port and otherwise communicate, then it is literally this fast. If it can't, it can take you a very long time. So the whole idea with this, of course, is that if you wanted a satellite that could fly and was ready, then you wouldn't have bought this project here. So this project is actually to teach you a little bit about all the different various things, and we try to make it not too impossible to get it right. So the software is, for example, ready-made, but you still have to do a number of different things here to configure and get it up and running. So as I said here, using drop-down select Xq7, which you did, and that's the same whether you have Xk90 or Xq7. That's what you choose. It's the same software. Click flash. It asks for the information as I showed you, and now you can power up the ground station. The rest of the information that's below is very optional all the way through. So I'm going to talk about it, but this is one of those things where, you know, once you kind of like got to this point where you power up the ground station and then flight station, you should be all right. I'm going to just talk a little bit about that, and I'm going to spend a little bit more time in the bottom where we talk about troubleshooting, so you're kind of like ready for if you have issues. So OwnTrack is a little mapping software that runs on either iPhone or Android. It's called OwnTrack. So it's not something we developed. And you can then configure it. The way you can configure it is you can scan this QR code here, and that will configure the QR tracks for your app. It can be a little difficult, so I really suggest that if you want to go down the route with this map here, read up on OwnTracks here and how it works. But this is the configuration file, and you can configure it manually. You don't have to configure like this, but this is just to make it a little bit easier. So why do we do this? Well, when your balloon flies, and you maybe follow the balloon in a car, so maybe you have a ground station. So what we normally do, if we put it on the balloon flies, we plan where the balloon goes. I can show you some of that also. But we plan where it goes, and then we take our cell phone and we make that a hotspot, and we connect the ground station to our cell phone as a hotspot. And then we follow in a car, we follow where the balloon drives. So when the balloon comes down, we're not too far away. And what OwnTracks do is that it actually puts the GPS that comes from the flight, it puts it on a map. It also puts your own thing on a map, so you can see where are you and where is the balloon. Now, it has to be said that both OwnTracks here is a live app. It doesn't use offline maps, and you have to be online. So if you drive a place where you lose 3G, 4G, LTE, phone connectivity, then all this is futile. So just make sure that you have connectivity when you do this thing here. And when you're sending a balloon up, that connectivity could be that you have another ground station that closer by, that you have at the varsity or whatever, and then you can actually maybe communicate using other radio methods to whoever follow in the car and say, listen, it's crossing that road now, and things like that. Okay, we have a question here. So Bokamoso, please unmute and let me have your questions.
Yes, the OwnTracks app, does it track the balloon itself, or it only tracks the ground station?
So it tracks the balloon. So the way it works is that the balloon have a GPS on board. Okay, so this is like my balloon thing. So the balloon have a GPS on board, and that GPS coordinate is of course where it flies, where it is. It sends the data using the radio to the ground station, and the ground station then uses a specific telegram, MQTT telegram. It sends to our MQTT server that's formatted in such a way that OwnTracks are then subscribing to it. And the OwnTracks is the OwnTracks on your phone. So that QR code, that configuration QR code, is actually to tell that it should look on our MQTT server. So MQTT server is a messaging server where you have the data, where the data comes in. So this QR code that is on the screen now is actually to tell that the ground, the on tracks, that it should look for the GPS coordinate on that specific server. So every time it comes in, it updates it. So it actually tracks the balloon. It doesn't track your car. But OwnTracks, of course, is running on a smartphone. They have a GPS already. So therefore, it also knows where the phone is. So on your phone, on the screen, when you run OwnTracks, you will see two symbols, one for the balloon and one for where you are right now yourself. So if you drive down a road, you should be able to see yourself on that road. And when the balloon flies like, 5 kilometers northwest for you, you should be seeing a symbol of that. So that's kind of like how it works. So you're able to track it. And the reason why you want to track it is because you can reach the radio that you have on this ground station is able to communicate over 2,000 kilometers away if it's like straight up, okay, if there's nothing in the way. So actually this is being used as a ground station for satellite tracking of current orbitals, lower satellites. I'm going to show you a link to that just now. So it can communicate quite far away. We have been able to communicate with a satellite over 240 kilometers away. But if it's 240 kilometers away, it's 3 degrees over horizon. And then it starts getting so low that you start losing it. So, but if it's just straight up or far up, then you can actually see it quite far away. We lost it 240 kilometers away. It hit the jet stream. It left over the south coast of South Africa, and then, was on our way to Australia. So we're never going to catch it anyhow. But we did actually get all the data. And on the dashboard, you also get all the data. So there's also a mapping facility on the dashboard where you can see it flies. But it's not mobile. So the whole idea for this OwnTracks is that you can follow in the car. And the whole reason for that is, as I said, once the satellite starts coming down, the balloon has exploded and the kit is coming down. Once it's coming down, you need to be closer by, because once it's below trees or mountains or something like that, then the rates drop very, very, very fast. So you only have this perfect range once there's nothing in between, Fresnel zone and all. So once it's kind of like coming down, you want to be close by in order to pick up the signal. Otherwise, it's going to be difficult to find your kids once it landed.
Okay, thank you so much. Because I tried to use the app because I don't know. We also did it when we were doing some drones because of the GPS data here. Some of the places are not well digitized, so I'm getting errors on my phone. That's number one. But if you can make a very short instructions on maybe how to get around this, that will be helpful.
Okay. Julie, will you make a note on that then?
The other thing that the other thing yesterday we had for the past 2 days we assembled the CubeSats and we tried to follow all the instructions. We had 2 sets running, but we noticed that the communication range between the ground station and the fire station, we need to put them very close to each other. So we are wondering the range.
Okay.
If you try to move a little bit, a few meters away, it starts to cut off. Yeah. I don't know what's the problem. Yeah.
Okay. So first of all, maybe what radio you have? What is it? ILO2?
You mean the RL?
Yeah.
It's RL01.
01. Okay.
Yeah.
So and what frequency did you put in when you programmed it?
The 01 is the 8. Is it the 868?
Yeah, no, it should be the 434.
From the drop-down menu is the 434. The R1, okay. RL01. Yeah.
Okay, so the thing is that for that purpose you need and because most of the people who've been using that have been using ILO 2 and ILO 3, we have actually done an update for ILO 1. So you have to actually put another piece of software in, and let me just find that. Hang on a second. Yeah, so let me just show you that. Share. So on an XinaBox upload, let me just share this thing here. So on an XinaBox uploader, you can see down here next to where it says V1 version 110C.
Yes.
If you click on this gray line, this is kind of like a secret button. It's actually the progress bar, bar, but I also use it as a button. If you click on it, like I did now, then a little beta appears next to it. Okay, and once that appears there, when you choose apps, you can see you have a much longer list of apps. So this is all our beta apps. This is what we use when we try to test different functionality. If you go down to X07 beta, that supports the ILO 1 radio. So just try to use the Xq7 beta down here.
All right.
But Judy, just remind me, I just want to make sure that all that what I'm saying now is correct. So I just want to forward get the latest instruction from Lukman and make sure they get that. But I think that your problem is that you have that the radio is actually trying to communicate, even though that you said ILO 1, I think it communicates 868, and that's actually your problem. That's the reason why you get that very short range. It's actually not able to communicate with the correct frequency. I just want to show you this thing here, but let me just make sure that I send you the correct instruction. It's just a matter of using another a version of the software that supports the ILO 1 properly.
Okay.
Okay. I just want to go back to this instruction very quickly. So I'm happy to hear that you have tried all the different things. So in any case, if you want to do your own dashboard, I'm not sure you want to do that, then the instruction here is how to retrieve the data from our MQTT server where it sends the data. So let's say, for example, for some reason, you want to put the data on an Azure or dashboard or some AWS or something like that, then you can get the data here. You can also see the data if you have like a MQTT kind of like tool on Windows, Mac, or I have one on my iPad. Then I actually put the data in here and do what it says here, and I can see the raw instruction also. The other thing I just want to say is that when the JSON data comes from the MQTT server, they come typically in two different packages. One with all the sensor data, and once it have a lock on the GPS, which is not necessarily happening immediately, then it also sends another record with the navigation data. So it comes in two different data streams. It comes in the same stream, but they're just two different JSONs that arrive. And then this is about the Cubesat interface here. So the main reason for the Cubesat interface is to allow you to interface with other Cubesat technologies. So for example, if you have like a battery technology with solar panel, or you want to use another computer core and you just want to use our stuff for the sensors, or you have another radio, you can actually interface that together this way. There's this interface control document, which is, I think, the typical name for that kind of stuff, which is a PDF that kind of like that talks about what is on the BS01 board. So this CubeSat bridge here, so this connector here. So you can see you can either put them together where you have 6 X chips in a configuration, and then it hangs over a little bit, will still be 10 centimeter and actually allowed in the original documentation, or you can have the kind of like the stuff where it's properly inside. Here is documentation about, the standard stacking height, which is from the PC104 documentation. And here I have the GD or Mauser codes for the different nuts and bolts. You can of course find them anywhere, but if M3 6mm stud doesn't give a proper description, you can always look it up in GD and then maybe find it on RS or your local hardware could. So this is how we put it together in the different layers. So just to kind of like explain what the different things are, there's like this support board underneath, which you don't have to use, but if you put in a satellite and rocket and all that kind of stuff, and you want to have it to hang properly together, then it's probably maybe a good idea to bolt it together. It takes forever to bolt it together and an equally long time to take it apart again. So I did it once when we created all this thing here. And then it's called PC104 because there's 104 connectors divided into H1 and H2. There's no real standard for how it's used other than the power. And when I say power, it's only the 5 volt and the ground that is in the standard PC104. There is an alternative power where we have 3.3 volt here. There is typical these 2 pins and these 2 pins used for I2C. We use them both, but you can configure which one you want to use by flagging a solder pin on the back. If you want to use the 5 volt, then you have to solder the 5 volt here on this little thing here, and your power on your you don't need it for all our sensors, all 3.3 volt. But let's say, for example, that you want to get 5 volt out, and you have a USB connected to our kit, and you want to get it out here, then you need to solder that. So here's the different pins per documentation. There's the electrical characteristics, and then there's on the back of the BS board. There's down here. There's 2 solder pins. The one is pre-soldered already for I2C application payload, I think. But you can choose if you wanted to use it for I2C payload or for I2C system. This is the 2 typical names that are being used. So because there's no standard, all this, what we have done is that we have got a lot of data sheet for all the different manufacturers that do PC104 stuff and figure out where do they typically put it together. There's also RX and TX, which you can communicate with. So for example, if you have your own core, you can maybe communicate to some of the other boards using UART. And our core, we also have you can also plug in USB-C, a Raspberry Pi Zero. So for example, I have a Raspberry Pi Zero here, and I have a little board. There's also one with a bigger board, and you can actually plug that in. And NASA have some software that's called, I can't remember what it's called now, but they have some software that you can put on, and then you can program that on a Raspberry Pi. So if you want to use the NASA software for this, it's open source, but it's just very, very heavy to get to use. But you can do that. So you can take a Raspberry Pi Zero, plug it in, configure the software, and you can use all the same hardware you have here. So that's that data sheet is about the CubeSat here, this control interface here. So as I said, we have a east, which is the main connector, and then you have a west, which is kind of like more supporting bracket that allows you to screw it together, and you have this backbone. It doesn't have anything. It's made of FR4, which is PCB is made of, but it doesn't do anything other than just give it structural integrity. Okay, so here I just want, and this is the main thing here, and then I think I'm just gonna kind of see what I can cover of other stuff. On troubleshooting, so the first thing here, if ILO1, if it has switches, so some of the radios have switches. I don't think the ILO1s have, but like for example, let me see what I got here. I don't have a radio, of course, here they have switches on, but some of the radio have switches. So like here I have a soil moisture sensor, and I have a switch down here.
Sorry,
so this is what it's
maybe stop sharing so we can see your camera. Sorry.
So you can see here that I have a soil moisture sensor, and that have like some switches. They're address selection that allows me to have multiple soil sensors in one circuit. Because there's 2 switches, allows me to have 4 in total. On the other radios that have like 3 switches, that allow you to have 8 radios in one circuit. Why would you do that? Well, it's kind of like more that you can. So therefore we have put in the switches. It's not in a earlier version, it was a newer version, and it's one of those things where I wish we haven't done it, because nobody uses it and it just creates confusion. But anyhow, the important part here is that the switches are phase and on position. I don't think you have that issue, so let me go further. If you're having a communication problem between a circuit, then try placing ground stand fly station 3 meters apart. So if you're running the radios and they work properly, then they can also be too close to each other. That's apparently not your guys' problem in Botswana. But if they were running the right software and it doesn't work, then that could be too close. Another thing that's important is that the antennas are monopole antennas. So they have to, if you, for example, plug something in, the ground station into your one side of the computer and the other into the other side of the computer, let's say you could do that. And the antenna points away from the computer, then they're actually standing back to each other, and then they can't see each other. So just make sure the antennas, if they're monopole antennas, which they are, then the antennas have to be parallel. If they're like that, they can't see each other. A monopole antenna can't see anything below its ground, so this way down, and it can't see anything just right in the middle on the top. It's kind of like if you can imagine an apple. So if you cut an apple in half, then the radiation goes like that. So radio that like that can see each other, not exactly like that. Like that, they can't, all the way to like this. If they're like that or like that, they can't see each other. So that's just important for this thing. So if you fly the balloon here, then make sure that your antenna on your balloon points down. And of course on the ground up, then they will be able to see each other without problem. Okay, so that's like just on the antenna side. If you get any message relating to the almanac, okay, so what we try to do here is that when the way GPS works is that you have almanac. And the almanac is kind of like a little calendar catalog, whatever you want to call it, a little configuration file that tells where all the satellites, all the GPS, but of course also all the other satellites, depending on where you get the file from, where all the GPS satellites are at any given moment. So it's kind of like celestial elements. You identify with the 2-line element or Kepler element to kind of like figure out where they are. It's similar for these GPS satellites, but of course they can move slightly. So you need to have this, they of course power these satellites so they can move around. But you need to have an idea about exactly where they are in order to get a signal, a triangulation of your coordinates. So what happens in a typical GPS installation is that if you're not connected to anything else in the satellites, then you're getting the data down from the satellites. But it's a one-way communication. Satellites send data, you can't send anything to that. So what it does is it keeps on sending, and it's a 3.5 kilobyte file. So it's not a lot of data, but they're really, really, really far away, these GPS satellites. So therefore, you might not be able to, and that, of course, it's a digital data. They have to be accurate. So it will send it out like in small blocks. And if you don't get all the blocks, you have to wait to send the next block again. So you sit there and wait and wait and wait. And when you have all the blocks, then you can reconstruct this almanac inside the GPS. And all that is happening automatically. We haven't done anything. This is just standard GPS stuff when you buy like a GPS. So this all happens inside this GPS module here. So what happens is that that data, once you have all the data, it's like, okay, now I'm getting these different signals from a number of different satellites. I know where they're meant to be because I have the almanac. And I can read the clock from the satellite, so I know this is where I have to look up in my table. and then you get a signal. Now, if you're outside and you're wide open space, there's no building there, trees or anything like that. You have like 160-degree open field around you. That shouldn't take much more than 5 minutes. In a rare situation, it maybe take 10, but that's the limit. So one of the things is that it can take longer time depending on where you are. There could be a lot of radio noise. There can be other kind of stuff that makes it difficult for you to get the signal. So what happens is that what we do is that we download the almanac over the internet. So the ground station downloads the almanac over the ground station, and then it tries to then send the almanac via the radio to the flight station. So from the ground station to the flight station, will send the almanac up and say, here's the almanac. It doesn't work perfectly. Actually, it doesn't work perfectly. That's very, very safe to say. So what many times happen is it comes out and say, sorry, I couldn't download the almanac. This was just kind of like to see if we could cut down the 5 minutes to 25 seconds, which we have, done a number of times. But if you get this thing here, don't stress. You just have to wait a little bit longer. The other thing is that don't compare the almanac on our system to what you have on your $1,000 cell phone. These ones are connected to the internet, it's integrated, downloaded, but also other system uses GPS, and not just GPS, but navigational satellite data, not only from GPS, but also from GLONASS and Baidu and all the others. This satellite receiver only takes GPS data, and therefore you have very few satellites to look for, which means that you have to have this clear view of the sky in order to get a proper signal. So I just want to say the stuff that there's most problems with here is of course radio. It's either the radio between the ground station and flat station or the GPS. Okay, so that's related to this thing here. The message here. So if you don't get it, don't worry. You get it from the sky. It just takes a little bit longer. And then there's this other story here. If you're not getting GPS signal, make sure you're outside and you have 160-degree unobstructed view of the sky. So 160, like that. And there's a little story about how this thing here works. There's an app I use to figure out where the GPS are on a sky. So I'm using this one. I have a phone. There's plenty of these ones. So I haven't found one for Android. I don't have an Android. I would know. But this GPS plane might also be there for Android. I don't know. But what it does is it shows a little kind of like picture of the sky, kind of like we know from when we look at stars. And it just plots out all the different satellites, both the GLONASS and GPS and Baidu, just have different colors so you can see which one is which. And then finally, you can also troubleshoot by plugging in the ground station. So for example, I have the ground station plugged in on my computer here. And the best way of doing that is that I'm here talking about that you can use PuTTY on Windows, you can use CoolTerm on Mac and all that kind of stuff. But you can also use the Arduino console, and that's what I prefer to actually use. So what I'm going to do now is I'm going to stop sharing this screen here, and then if I am, I just want to connect here to my, here we go, and I want to show that. Hang on a second. We have share screen there. So here on this is the console from Arduino. So I haven't plugged in anything. So it's gonna go in and say error and all that kind of stuff. But what I'm trying to say is that you can see here that it connected to the server and now it crashes because of there's nothing connected to it. So that's fine. I'm going to stop this auto scroll here. But you can see when it starts up, it tried to do a provisioning. It will go in and say it didn't get anything, obviously, because you're provisioned already. The complaint, there's no ODR1, there's no radio, which is like the two major things you want on a ground station. And it goes in and complain. But if you have all things installed and things like that, you'll be able to actually see a lot more data here. So we kind of like write out a lot of data. You just have to make sure the boot speed is 115/200, and every time you start and stop your console, it actually sends a reset signal to the device. So therefore, it automatically reboots when you open the console. I just want to make sure you understand that. But that's, and by the way, you can do the same with the CS11 if you have a programmer. You could also plug that in, and of course, we also have data coming out here that we use for our own stuff. So just maybe an extra opportunity for troubleshooting. So I think that is it. Just a couple of more things. Let me just share the screen here. Here. So one of the things I find like that is quite important here is understanding how this radio works. And one of the things is that if you go to youtube.com/XinaBox, then there's a lot of videos that are done over time. There's a playlist here. Called Xtips Daily, which I started doing last year when the lockdown started. So you'll be able to see here like stuff, especially around radio and programming and things like that. So here's a lot about TPS. There's a little bit about I2C. Here I'm going into to the radio here. So I'm just gonna kill that. And there were live streams, so that they can be long and they're not edited and things like that. But there's a lot of stuff about, you know, the different radios, frequencies, how they use it, what lure is. If you want to make your own antenna, you know, what you should get and buy, how they're connected. There's a little bit about how to do a link budget. For example, I have this little diagram here to kind of like show the link budgets. And I calculate the link budget and why you can connect. There's a link budget calculator, which is online. It's not anything I've done, but I'm using it in this video here. So there's a lot of material, and then also this thing about how far you can see over the horizon. So there's like this calculator that show, you know, how high you have to be up before the Earth's curvature is playing in. So I just want to add that, you know, look at some of these videos also. They are they're going to help a lot. There's specific data about radio. There's also one about GPS. That's great. And then, of course, last one and not least, which I just want to show also. If you go to GitHub, well, so a couple of things. First of all, you have a CW1 and you have an IPO1 that allows you to program and do your own programming of a lot of different things. So if you go to github.com/XinaBox, then there's a number of different libraries. And if you go to, for example, if you go to the CW1 library here, it's a CW1, then there's a little file here that's called CW1. So don't worry about the ones that's called something else, CW1. The CW1 here will tell you exactly what you have to do in order to program the CW1 in Arduino. There's a video here that explains it. You need the programmer, you probably have the IPO1, you need to install Arduino, there's a link to that. You have to install this ESP8266 core, so that's what behind this thing here. And then there's a description of the pins that you need to understand inside the Arduino code. So if you want to program the CW1 and some of the sensors from the flight station, you can do that. So you have a full opportunity to program this thing here directly. Yeah, that is. Oh yeah, and then the final thing is the Xq7 software itself. So if you, so the software we use for the Xq7, so the one you download on your using XinaBox uploader, if you want to modify it, we will make it available for you. But we don't support your attempt to modify it. Let's put it that way. It's a very big application. Of course, it takes hand of all this kind of stuff, and we have people at, I think, Princeton. They have modified themselves. Stanford University, that did a modification, things like that. But we, if you want to do it, then you better be, ready to program in Arduino and have that under control. You can't just modify a little bit and then send it to us and say, please compile it for us. So you're on your own, and therefore it's not completely open. We will let you in, and you can then do a pull request or fork the code, whatever you want to do. And we of course encourage you to it, but we want to make sure that you really want to do this. If you want to do it, then make yourself a account on GitHub and send me your handle, or send Judy the handle, and I will add you to the group that will have access to the code. But that allows you to then get access to both the ground station and fly station code. So let's say, for example, that you decided that, hey, we want to use the particle matter sensor and we want to do your own code. Or let's say, for example, you want to do something with other GitHub stuff, but you need to modify it to use it, or you plug something into the XinaBox, into the PC104 connector. Maybe you had like some other little device, like for example, I have here a little sensor here from Adafruit. Is like a Rtb sensor. Let's say you plug that in with a breadboard to the PC104, but you want to include it in the code. Well, there's, it's Adafruit, so they probably have done a nice library on GitHub, but you just have to do that modification yourself. So it's open source in that sense. We're just careful that we're not just giving to people and people think there is a lot of support to that. That's great. Thanks, Judy. Yeah, Judy, if there's more, then let me know. Otherwise, let's get understand the RL1. So I will get the instructions from Lukman and make sure that the guys get that for the RL1. I will look at this own tracks. Maybe actually ask Lukman to do a little introduction to get own tracks to work. And then I think that was what's on my list that came out of this thing here. Otherwise, Judy, over to you.
Bjarke, thank you very much. Yes, I've made a list of that. And then what I've been doing is that I've been capturing a number of the points and links, etc., that you made in the chat. And what I will do is when I share the video, I will also share the text of the chat as well. So please, this is your opportunity to ask the questions, because any question that anybody asks informs everybody else. So yeah, please ask Bjarke questions, because if I leave Bjarke to speak, he will keep speaking for 2 weeks. So yeah, we need to make sure that it's question driven.
Judy, I just want to think before, also I haven't covered anything about the dashboard, just so you know, as you've seen. So if you want to cover the dashboard or anything like that, then feel free. Okay.
Okay, one question I saw on your casing. Is it possible to upload our own logo? Because I only saw your XinaBox logo.
Yeah, so it's quite interesting. There's in the software, there's no option for uploading your own logo. But what they did at Stanford is that they downloaded the STL file. Or you can also, I think there's other files you can download. So it doesn't only STL file. There's also something else, and then you can use like an open source 3D program to go in and put your logo in. So the software. So I didn't do all the software here. Just I took some existing type software out there, and then I wrapped this around. And that software didn't have an option to upload, which kind of like annoys me, because I would have loved there was an upload option. Also because then I could have different kind of like enclosure styles that maybe I started with. But there was no option for that, and I wasn't going to spend time programming that. So what they did at Stanford was that they built a box the way they wanted. Then I downloaded it, and then I used Tinkercad or something like that. And I went in and I just took their own logo. They probably had a vector graphic of the logo like SVG or AI or EPS. And I just extruded a little bit and put it into to the box. So that's the way to do that. And absolutely, you're welcome. It's just, we didn't have an option to do that. So.
Cool. Let me give a chance to the other students to ask questions.
Yes.
Maybe everything's ready to fly tomorrow. Let's start filling the balloon with helium.
Yeah, there's helium balloons. So where do you get them? Because we don't have such here. I mean, is it just a normal balloon from the balloon shops? Is it okay?
Yeah. So
okay,
yeah. So there's a balloon shop. The way where we get them is that there's a Judy and I in Cape Town. Where we get the balloon is that there's a balloon shop in Durban. They have them there, and I assume that will send to you guys also. I just got an email from them today. They had closed the shop because of the unrest in KwaZulu-Natal. So they're not shipping any balloons now. That I can promise you. I got an email here earlier today. So but the balloon you can get there, and it's also possible. I'm just saying it's not the best, but it's get smaller balloons and just fill helium in more of them. So you can take 2 or 3 smaller balloons. It's a little bit more complicated to calculate, how much it expands and therefore how far it will fly and all that kind of stuff. So I wouldn't suggest that. But the guys in balloon, and Judy maybe just send a link to the guys in Durban. They have like balloons that go up to 1 meter in diameter. This is not a meter, but my camera is. Here we go. So that's what we used. And by the way, we got our logo printed on them. So you can, if that's important for the PR part of this project, then I think for a small fee they will print your logo on, I think in black on either red or white balloons. I think that's the 2 colors, so you can choose in those big ones. So we of course had white balloons with our black logo printed on them. And Julia put in the link in the chat, so there it is.
Okay. Another question. When you fly this balloon, are you getting any kind of restrictions from your local regulators, especially the aviation?
No. So the thing is that even in the US, where FAA is hardcore about regulation, the reason why you're not really getting any problem is because what you fly is very light. So you're flying something that maximum weighs 150 grams. And 150 grams, the most heavy in your circuit is your AA batteries. And I think our kit with a frame is maybe 114 grams or something like that. So I say 150. And most of the places in the world, they have accepted that you can, for example, fly a drone unless they're just not allowed to weigh more than 250 grams. So for example, DJI makes a small drone that weighs 249 grams, so you can fly it most places. What we used to do is that there is a website for the South African Civil Aviation Authority where you can go in and tell you want to fly, and you can give your GPS coordinates of flying and all that kind of stuff. But I mean, they're not really responsive to any of this kind of stuff. We have maybe done it once, but many times when we fly, we just fly the balloon, and it is within the law because of the weight and its balloon. So a balloon has also another thing. So for example, a normal hot air balloon, with people flying in, they have first right in the sky because they can't really control it. So if you're an airplane, you have to give away for a hot air balloon. So you can say the same thing with these party balloons. So we don't really have a problem. I know in the US, they never do anything about these balloons. Normally they fly to, if you pump it correctly and things like that, they fly to 5 kilometers. But, if you have a big balloon, very light kit, and you just fill in enough helium that it can lift, then it will, first of all, go very slowly up. Second of all, it can get much higher up because, of course, it can expand much more because the balloon was maybe a big balloon in the first place. So our record is like just over 12 kilometers, I think, which, of course, is higher than commercial aircraft which fly in 10 kilometers typically. So that's the thing. What I actually just want to show you is, let me just share that, is a website. So when you want to fly, there is the Cambridge University, sorry, here we go. Cambridge University have done a software that's called HapHop Predictor. So HapHop is so CUSF is Cambridge University's a satellite flight something. So they have like these different calculators. So they have this predictor here, and it starts in the US, but you can zoom out and then scroll down to Botswana. So let's go here. I assume you're in Gaborone. Maybe I shouldn't assume that, but you can do that. And then you can say, set with map and say, listen, let's launch from there. And then if you do it right now, and you say you go to, say, 10,000 kilometers, and then you run prediction, then it will tell you how you will
10,000
fly.
meters,
Okay?
not kilometers.
10,000 meters, sorry. And you can see, well, the way the wind are. And if you look a little bit, you can see here how it flies in one direction when it goes up, and then it goes, it changes direction, and then the little explosion is where it predicts the balloon is gonna explode, and then it's gonna land in South Africa here. Okay, so of course with this kind of like, and this you can calculate up to a week into the future. So if we say, for example, on the 19th, we want to do this thing here instead, and then we say run the predictor, then you can see it stays inside. Now it flies in and lands in the central business district here. Okay, but that's of course if your ascent rate is 5 and your descent rate is 5. And the descent rate, that's calculated on a parachute. There's another calculator that will tell you that if you weigh so much and you have a parachute that have this area, it will descend with this speed. The ascent rate is again, something you can calculate if you know balloon and all that kind of stuff. So there's like some, and then the burst altitude, that's again the helium and the balloon and all that. Some of this, for us, what we do is that we say, well, this is the general direction. And if you, for example, say we want to land, here in this area here, then we will, just go and say, well, let's drive out here and then launch from this place. Run the prediction, and then, it's kind of like lands hopefully where we expected. And you can see, there's a little road. Hopefully you will have somebody in this intersection that have to go in here and out again and follow the road and then out there. So that's, and the reason why we had the OC01 is that what we did is that if you get yourself like a buzzer or something like that, that doesn't include, but like just a buzzer, then it will actually beep. So when the balloon lands, then the idea is that the accelerometer will tell I'm not moving anymore. The accelerometer is like steady at 1G, and therefore it will then start beeping once it landed, so you can find it by sound. You could also put a infrared LED on it instead, a resistor infrared LED, and of course it'll blink, and that you can see if you fly a drone over it, because the camera on the drone, you can put a colorful LED on it, like a red one, and you can find it in the middle of the night, and there's a number of different options. So so that's kind of like the idea. Yes, Judy?
Bjarke, we have a question here. Is it possible to do a constellation using one ground station? In other words, multiple flight stations and one ground station?
Yeah, try it out. Normally, it's the other way around. Normally, you want one flight station and multiple ground station, because you want to have maybe somebody where you launch the balloon, so you get a signal. You might want to have somebody on the roof of your institution, so you have like a slightly high point, and then maybe you have somebody down the road and where you expect a balloon coming in. So that's kind of like more the way we're using it, is that we have multiple ground station and multiple flight station. The problem is that you don't know where the data comes from. So a number of years ago, we had a project with NOAA. So NOAA is the North American climate organization.
Ocean
so
and atmosphere.
Okay, those guys, NOAA. Yeah. And we did that in where they have the data center in Asheville in North Carolina in the US. And they had like a lot of schools, and each school wanted to fly. And back then we had a modification on the software where we could send a radio ID. So each radio will send a radio ID. But we took that away because then you had to add in the configuration. People couldn't understand it, didn't know what it was. So we kind of like eliminated it from the software again. And in any case, it ended up that didn't fly at the same time because they couldn't handle all the flights at the same time and pick them up. You have to remember, we put on a balloon and the flight, there's a good chance that you're not getting it back. And it's maybe not the cheapest thing just to throw away. Maybe people are nicer if you put a sticker on it. Then when they see it, they will call you and say they find it. Okay, but now Botswana is not the most populated places in the world, so nobody might come across it where it lands. So you can have it safely somewhere landing, but if you can't find it, it might be there for some generations. So what I suggest is that just do one flight at a time, but maybe more consider multiple ground stations rather than multiple flight stations. If it's going into space, that's actually another thing I wanted to just show here. So I'm very happy with these questions. Sorry, I need to share my screen here. So there's a website here called tinygroundstation.gs.org, I think it is. Let me just check. It could be .com. So what this is that this is ground stations that is being put up around the world, as you can see in this map here. And they follow satellites, like for example this Norby here, which is a LoRa ground station. Sorry, LoRa satellites. So if you go here and say stations, you can see there's different stations, different places, and they're listening to typical this Norby satellite. There's a lot of them coming up, but right now there's not a lot. And you can see here what they last picked up and how many signals they pick up. What's interesting is that they use now this one here this satellite here, Norby here, I think it's this is how it looks like. You can see that runs on 436. So that is the ILO1 radio. So you can listen to that thing here, and many of the ground station is built around the ILO1. Now you need special software and things like that you can install from these guys. But the main reason why I want to show this thing here is not because necessarily you can listen to it, but if I take, for example, this package here. So here is here. This is somebody in probably the Netherlands somewhere. They listen to satellites. You can see here that the distance between a satellite and a ground station, and when I say it's the same as ILO1, it's exactly that chip that sits on the back of ILO1. They're using to listen to a satellite that is 2,822 kilometers away. It's only flying 400 kilometer, Leo, 400 kilometers, something like that, in altitude. But because it's not straight over your head, but to the side, like here, then you start adding a lot of distance. And they listen to that. They're not going to use the same antenna you have, but typically people build their own antenna. So they have like a ground plane antenna or something like that to put up, which is like omnidirectional. So it's not like even any kind of special antenna, things like that. But this tinyds.com here, I strongly suggest you go and look at that as a way of where's my stop here? I want to put it in there. Is it possible to reprogram the radio unit ILO1? So the only thing you program here is the CW1 and the CS11. They're the only two cores. But if you want to program, make a program for the ILO1, so let's start with that assumption. You go to GitHub again, and then we have a library for the radio, so XinaBox. And there's something called ILOX, I think, so let's just say IL here. Yeah, ILOX, yeah. So this is the library that we developed for the radios. So you can see there's an example here. I can't remember the 8 months ago, yeah. So there's an IL radio here, and that kind of like the one is meant to receive, and you can see here that's set up to connect, to receive with, and there's like some modem configuration and things like that. So this one here has been set to the ILO3 frequency, but you can set it to whatever frequency you want. So you can actually use this to connect to program the IL. So this is an Arduino library. There is a very specific thing about the radio. So I have well, let's see here if I have a radio here. No, I have another radio here. So, but on the back of the radio, this module is the one module I'll talk about in TinyJS, as you also have on the back of yours. I have a version here called IL13. It's not like something we're selling, it's something we're experimenting on. It's using this IPEX or UFL antenna instead of a SMA. The important part is this fellow that sits here in the front, that converts from SPI to I2C. So this radio here runs SPI in a standard configuration. And because our bus standard is I2C, we put this little converter chip on and convert the radio stuff here to I2C. What it also do is it have a number of extra GPIO pins on this. And that's great because the ILO1 not only uses SPI, it also uses like 2 or 3 other GPIO pins. They have something, of course, have chip select, which you use in SPI, but they also have 3 GPIO pin you also want to use. So this converter chip also do that. So you talk to it in I2C to this one here, and then it converts it to this one here. So therefore, you can't use other libraries. And I just want to share the screen here. So if you want to program using the ILO1, then you can you can do that. You can program your CW1, and you can use this example here. So if you, for example, let's say you and a classmate want to test it out, you can take one ILA1 and one CW1 and program the server and then the client, and then you can communicate between the two and kind of like get the idea how it works. So that's the way you program that. Now, the reason I'm saying what I'm saying with the sensors is, for example, if you take like the SW1, now you can see here that we have an Arduino SW1 here, and the SW1 uses this BME 280 sensor here, okay? And if you want to know what sensor your board uses, because you want to use another library, you go to XinaBox products, but you can just do it directly here. So if I take, for example, what we take, SW now, SW3, yeah, let's take SW1. Let's take SW1. So it says this page not fun, but it jumps there. It was still in a bracket here behind what module you're using. So we call it SW1, but that sensor that sits there in the middle is BME 280. If I do it with number 2, then you can see it's a BME 680. So if you then go to GitHub, then you can actually search GitHub for libraries here, and you can see Boss SensorTech who makes it have done one, Adafruit have done one, and then you have actually this library here. Of course, the hardware looks different, but the libraries works equally fine, so you don't have to use our library. So why will you do that? Well, for example, if you take, let's just take the BME 280, BME 280 here. Sorry, we need to say all. There we go. So if I take this one here, then there's an Adafruit library here, and there's examples, and they have like 2 or 3 examples here. But one of the nice things is that if you go to, for example, SparkFun, you also typically do libraries for these different. So here's a SparkFun library. Then I typically have more examples. Let's see if I'm lucky. Yes, here you can see there's a lot more examples there. So if you see, for example, oh, this one here can do CSV output or relative altitude change or something else you like, well, then use that library. You don't have to use our library. And that you can do on almost every of the except 2. The one you can't do it with is actually 3. One you can't do it with is the radio, because it have this converter on it. The other you can't do it with, and you don't have that properly, is the particle matter sensor. That is running serial, and because of that, we have a little converter that converts serial to I2C. Because it runs serial, and because the CW1 also runs serial, you can override it here and communicate it with it anyhow this way. And the last one that have that problem is actually the GPS. And the reason for that is that GPS communicates I2C directly from the sensor, but it also communicates using UART as a serial. And the interesting part is that nobody uses I2C, they all use serial. So if you find a library that want to read it serial way, well, you can do that. There's a little solder thing up here in the corner, so you can activate it up here so you can get that to work. All other of our sensors or displays or whatever you find, they use I2C. And there you can just use any library directly. With those 3, you maybe have to fumble a little bit.
Great.
Sorry, Judy, there's another question here. To reset CW1, that was what you wrote here. Is it possible to reset the CW1 card? My mic is not working, or I don't know what mic is.
Microphone.
No. Yeah, but there's no microphone on CW1. You don't have a microphone at all.
Bianca, the reason why I've unmuted myself is that
Yes.
in 11 minutes, I need to go and I'm recording this. So what I was thinking is, I'm very happy to make you the host, but at the top of the hour, the recording's going to stop.
Yeah.
So
but let's figure out how much more there is. I mean, as you said, I can keep talking, but I want to just address if there's any specific question.
I think we have exhausted most of the questions that we have. And the question that was asked was, is it possible to reset this CW, is it CW01?
Yeah.
Yeah, and then they said the mic is not working, meaning the computer's mic is not working, so they cannot.
Okay.
Yeah.
That's perfect. Yes, sorry. The CW1 doesn't have a reset button on it. But it's not impossible to reset it. So first of all, the best way of resetting is, I think Judy said, is you just recycle the power. You can't reset it like you can reset it in the code. So if you want to do it in the code, you can go in the sleeping, and the way it wakes up from sleeping is actually it issues a reset to itself. So you can put it into sleeping for like a second, then it resets itself after a second and wakes up again. So if you want to do it in the code, you can do it that way, or you can power cycle it. Also, you can do it using if you connect, for example, to a serial console, then it will reset every time you connect the console. So, and the reason for that is the DTR and RTS pins that's connected resets it. So you could actually kind of like make yourself a Python program that use RTS and DTS to reset. You can do it that way. You can run ESP tool, so you can download ESP tool or install ESP tool. Just put the name in there in the chat. So that is like a Python thing. So you can say pip install ESP tool, and then you can run that. So you can do that with Python -m ESP tool like that, and then it will come out and tell you how to use that. And one of them there is that you can reset. You can load software into the ESP tool. You just get the MAC address and things like that, all that kind of stuff. And by the way, I also talked about the MAC address 1 second with that. If you try to connect everything to your Wi-Fi at the university, and your university have like, a secure connection where it uses enterprise Wi-Fi, or it uses like, say, a hotspot interface. So it's not like the same kind of like Wi-Fi as you have at home. Then many institutions like that, they will have an IT department where if you give them the MAC address, it will accept your device, so it just connects. So if you can't connect the normal way with Wi-Fi, then ask your IT department, if you give them the MAC address, if they can then allow it to be connected. It's a typical thing for Internet of Things style stuff, because a lot of Internet of Things doesn't have, a screen or keyboard or all that kind of stuff that you normally use when you connect to Wi-Fi. So the MAC address, and that's the reason why the MAC address comes out when you use the XinaBox uploader and you give that to your IT department. So we know that have worked for a number of different institutions that have, extraordinary high security. Otherwise, you can use your phone as a hotspot. It's a very, very little data that comes over this thing here, because it's just like a JSON telegram once a second. So it's not like downloading a HD movie or anything like that. So yes.
Okay. Yeah, just to make a follow-up on that. The reason why they're asking the question is because last time when we were setting up different kits around, or stations, so there was kind of I think kind of interference, or we didn't know which station is connected to which one. And then we had a fallback to the older version of the Xq7 version 14.01. so that's the one we flashed in so that we can go and choose the radio links.
Okay.
So I think now to go back after that, for you to go back, it was kind of, how do you reset all these things? But I think you have answered us.
Okay.
But the other thing is, can I ask, I have a team of students who are doing the altitude determination control system here. Have you ever had any team attaching that kind of system onto this and seeing how they can control the system with while you have the balloon attached to the CubeSat?
Yeah. So most of the teams that using our technology, using it like as it is, they're not really connecting a lot of other stuff to it. They're kind of like, I mean, the idea with that we have as a CubeSat is that if you have a attitude controller determination system you want to connect using the bus, then you can of course do that. You have to program it and all that kind of stuff. I don't see any problem in it. I mean, it again depends on how you have to communicate to that attitude control system. So if it doesn't use I2C, which there's a good chance it doesn't, but hopefully it communicates using the serial port and it connected to the correct wires of the PC104. So if you want to do that, there, and of course also another option is that you don't want to do control, just determination. So attitude determination system alone. You know, with IMU, you should be able to kind of like get some of the information out of the IMU of in which direction it points. Obviously, if you want to use reaction wheels or you know, torque, magnet torque, or all that kind of stuff, then you're a little bit on your own there, both software-wise and hardware-wise, I have to say. So we don't have, I mean, Judy, you don't have anybody who have that have done anything like that. So so typically, I mean, yeah.
Sorry, Bianca, what I would suggest is why don't I actually just set up a conversation with University of Southern Maine, because what they've done is that they've modified their kits to be able to perform different experiments.
I think that would be
but
great.
I'm not aware of exactly what it is, but I think that it would be a really great relationship to foster, because they have done a number of things, and and let's share some ideas. If it's okay, is it all right if I leave? Bianca, I've made you the host, so you can carry on.
Which university is that again?
University of Southern Maine.
Okay, thank you.
So that's Maine in the US. I'm going to introduce you to the head of the faculty there, Scott Eaton. He's fantastic, and they've done some really innovative things. They've used the XinaBox chips in applications that we hadn't even thought of, and we only found out about it after the fact. So I'm definitely going to introduce you to him.
They also flown it. We have a relationship with a rocket company up there that have started a new rocket, so they're still flying suborbital. So they actually put the kit on a rocket up there that that you might also be interested in. So yeah.
Great. So Bianca, if it's okay, I'm terribly sorry. I'm going to leave, but I'm going to hand it over to you, Bianca, and we can arrange more of these workshops. Just let us know. If you're going to do a balloon launch, please let us get together at least a week beforehand. Okay. So if that's all right.
I think we can end the meeting right now, because the student says they have exhausted all their questions. I think.
Okay.
That's great.
Sorry for holding you for long.
No. It's fantastic.
Absolutely.
Thoroughly enjoy it.
It's been our pleasure.
Yes.
Thank you very much.
Let's do it again soon.
Yeah. All right.
Absolutely.
Thank you so much.
Great.
Thanks, guys.
Everyone.
Enjoy.
Thanks.
Bye.
Bye. Bye now.
Bye.